guys? Welcome back to another Algebra 2 lesson here with Mr. Gaines as we start to move forward into our discovery of exponential and logarithmic functions, and now getting into logarithms and logarithmic functions. Today we are going to focus on how logarithms relate to exponential equations. So in order to do so, we're going to go ahead and use a graph to kind of set up a representation. So here it says given f of x equals 2 to the x power, sketch the graph of f of x and the inverse of f of x. So if I'm going to sketch f of x, it's going to have a horizontal asymptote here. So this is y equals 2 to the x power. It's going to have a horizontal asymptote at y equals 0. There are no transformations, so its initial point would be at 0, 1. If I move to the right, it would be 2 to the first power above the asymptote. If I move to the right again, it'd be 2 to the second power above the asymptote. If I move to the right again, it would be 2 to the third power above the asymptote. If I move to the left of that initial point, so going back to 0, 1, if I move left 1, it would be 2 to the negative first power from above the asymptote, and 2 to the negative second power, and so on and so forth. And so we can draw in this curve for y equals f of x. And so this is 2 to the x power. So this is something that we know how to graph. We can also graph this using our graphing calculator. We know that over here to the left, it's going to approach this asymptote and do a great job of drawing that in, but it's going to get closer and closer and closer to this asymptote without ever intersecting it. Now, the inverse of f of x, if you remember back to inverse functions or inverse operations, what they do is they take the x and the y coordinates and they flip-flop them. So I have this point right here that is 3, 8. The x and the y would switch, so now I would have a point 8, 3. I have this point here at 2, 4. The x and y would switch, giving me a point at 4, 2. I have a point here at 0, 1, which would switch, giving me this point 1, 0. I have a point at negative 1, 1 half, which would become 1 half negative 1. I have a point negative 2, 1 fourth, which would become 1 fourth negative 2. And what we can see is the shape of a very similar curve starting to take place here. And so this curve is actually, as we know, based on what we've learned about it, inverse functions, is a reflection across the line y equals x. So this is the inverse of f of x. So what we may notice here is that it doesn't have a horizontal asymptote. It now has a vertical asymptote. A vertical asymptote of x equals 0. This would be a logarithmic function. So some things that we can see here is that the initial point has moved from 0, 1 to 1, 0. The horizontal asymptote has turned into a vertical asymptote. So now our exponential growth in this case is a horizontal exponential growth. It's moving faster and faster and faster to the right as I move up 1 unit. So the inverse of an exponential function is a logarithmic function. And we can set up kind of a definition for logarithmic functions or logarithms based on that of an exponential equation. So for any x and b that are positive real numbers, note this positive here with the double R means positive real numbers, so greater than 0. And b not equal to 1, it's our base, it can't be 1. Y equals log base b of x if and only if x equals b to the y power. So what we see here is we see some of the same pieces in our logarithmic equation that we see in our exponential equation. So the base stays as the same number. It is now written as a subscript to logarithm if I'm going to put this into logarithmic form. The input function, or the input value, which in this case was y, now becomes the output. And we know that to be true because we said that logarithms and exponentials are inverses of one another, and that's what inverse operations do. The output, x, for the exponential equation now becomes the input, x, for the logarithmic equation. So what a logarithm is a way of rewriting an exponential equation in a manner that gives us new inputs and outputs. It switches the inputs and the outputs. So in problem 2, it says write a description for each of the following equations, then convert to exponential form. So a description would be how that we would talk about this. So how I could represent this problem, this equation, or this representation A would be 3 is equal to log base 2 of 8. So that's how we would describe this, how we would talk about this equation. 3 is equal to log base 2 of 8. Well, how do we convert that to exponential form? Well, our base is 2. What was the output now becomes the input for an exponential expression, 2 to the third power. What was the input of the exponential or the logarithm now becomes the output of the exponential function. So 2 to the third power is equal to 8. And we know this to be true. We know 2 to the third is 8. Let's take a look at another example. So in B, I could describe this as negative 2 is equal to log base 3 of 1 over 9. And if we want to put this into exponential form, our base is 3. We wrote that down. The output of the logarithm becomes the input of the exponential, which is the exponent. And the input of the logarithm becomes the output of the exponential function, which is 1 over 9. And again, we know that 3 to the negative second power is 1/9. At this point, go ahead and pause the video and see if you can complete C. So C, I could describe C as 0 is equal to log base E, or Euler's number, of 1. And so hopefully that's the same thing that you had written down. Now if you want to put this into exponential form, again, our base is E, or Euler's number. Our original output for the logarithm becomes the input or the exponent for the exponential form, and the input of the logarithm becomes the output of the exponential form. And we know this to be true. E to the 0 power is certainly 1. So what we can do is we can switch between forms of a logarithmic function and an exponential function. Now let's take a look at a separate example where now we're in exponential form. So same concept here, write a description. So we would say, in this case, for 3a, 10 to the third power is equal to 1,000. Or, so 10 to the third power is equal to 1,000. We know that this is true, 10 times 10 times 10. How do we put this into logarithmic form? Well, 10 is our base. So I'm going to have log base 10. And we're eventually going to see some shortcuts for certain bases. Actually, in problem C, log base E is something special. And problem 3a, log base 10, would also be something slightly special. But our base becomes a subscript of the log. So 10 is the base. The third power, the 3, is the input for the exponential function, which becomes the output for the logarithmic function. The output for the exponential function, 1,000, becomes the input for the logarithmic function. So log base 10, I didn't give a lot of room there, but you can see that log base 10 of 1,000 is equal to 3. And this is something that we could check in our calculator. We're going to get to the specifics of how we would do that for too long. But for right now, we're focused on just rewriting. So let's see problem 3b. Again, the verbiage of this we should be familiar with. 9 to the negative 1/2 power is equal to 1/3. And again, we know this to be true because the negative would be the reciprocal 1 over 9, and 1/2 would square root that, so the square root of 1 over 9 is 1 over 3. Now writing this in logarithmic form. This would be log. Our base is the 9, so the base of the exponent is also the base of the logarithm. Our input for the logarithm, what we want to put in parentheses here, would be the output for the exponential function, 1 over 3. Then our output for the logarithmic function would be the input for the exponential function, or the exponent. So log base 9 of 1/3 is equal to negative 1/2. So again, what we're doing here is we're noting the expression the way it's given, taking a look at the verbiage, and then going ahead and switching forms. So we can switch from the exponential to the logarithmic form. See if you can complete problem 3c. Hopefully you've gotten a chance to complete problem number 3c. So what we have here is that Euler's number e to the second power is approximately sorry, I spelled this wrong. Is approximately 7.389. So that double kind of squiggly equal signs there means approximately. So e to the second power is approximately 7.389. So now our base is e, so we're going to have log base e, so the e is the subscript of the logarithm. Our output becomes the input, 7.389, and this is going to be approximately 2. So our input, the exponent, becomes our new output. So log base e of 7.389 is approximately 2. And hopefully this is what you had there. Now I did say that log base e is a special notation. This is actually what we call the natural log. So a different way to write log base e is ln, which means natural logarithm. And you may have heard me already shortening the word logarithm to log. That is pretty common. So the ln is the natural logarithm or natural log, which can be done in the calculator. So if we take a look at our calculator, that button is right next to the 4. So I can put in ln, natural log, of 7.389 and see that it is very near. It's approximately 2. So log base e is the natural logarithm. So what we're doing here is we're rewriting logarithmic form into exponential form and exponential form into logarithmic form. So they are inverses of one another, and we can convert back from one form to the other. And we're going to find this to be useful as we move into certain scenarios. Let's take a little look at a little bit further explanation, or exploration. In problem number 4, it says determine the value of each of the following logarithms without the use of a calculator. So we want to know what log base 2 of 8 is in problem A. This is log base 2 of 8. Well, in order to do this, what we're looking for is an output value. We don't know this output value, so let this equal x. What I can do here is I can rewrite the equation into a format that we can solve, or an exponential equation. So my base in this instance is 2. I don't know what the output was. I labeled that as x. That becomes the input when I switch to exponential form. So 2 to the x power is going to equal what was my input for my logarithm, or 8. So 2 to the x power is 8. We can then use the uniqueness property and rewrite 8 as 2 to the third power. And in this case, x would equal 3. So log base 2 of 8 is equal to 3. And there is a way to check this in the calculator with the change of base formula, but we're not quite there yet. So we're just going to stick to finding these. Let's take a look at another example. So again, in B, I'll make this equal to y. I'm going to change my variable. Doesn't matter what you make the variable, we want to know what y is. Well, we don't know how to solve this logarithmic equation the way that it's written, but we do know how to rewrite. So the base in this case is 5. My output y becomes the exponent, or my input when I switch forms. And my input 1 over 25 becomes the output when I switch forms. So I can see that 5 to the y power is equal to 1 over 25. Well, I know that 25 to the negative first power is the same as 1 over 25. And 5 to the second power is the same as 25. So 5 to the y power would have to be equal to 5 to the negative second power here. So y, or this expression, would equal negative 2. Let's take a look at one more example together here. In C, actually, we'll do both of these examples together. So C, again, I'm trying to figure out what this output is. I don't know what it is right now, but I can switch it into exponential form. So my base here is E. So E, my output becomes the exponent. My output in logarithmic form becomes the exponent in exponential form. And then my input in logarithmic form, E, becomes the output in exponential form. So this would be e to the first power, since there's no exponent written there. I have the same bases. So this would be 1. So log base e of e is equal to 1. And let's do one more together, d. So here, if I rewrite, let's pause at this point and let you try to rewrite. So hopefully you were able to rewrite the equation. The base would be 10. The output a becomes the exponent, and 10 to the a power would be equal to the square root of 10. So now to solve this, what I can do is change the square root of 10 into an exponent. So we should know that the square root is the same as the rational exponent, 1/2, and therefore a would have to equal 1/2. So log base 10 of the square root of 10 is 1/2. So in some instances where we have to evaluate for a logarithm, we can convert that logarithmic equation into an exponential equation, and then we are able to evaluate. Now, in some instances, we can evaluate or approximate the evaluation of a logarithm using the calculator. So notice that in 5, none of these logarithms have a base written for us. If a base is not there, it is assumed, or we can assume or write this as log base 10. So I told you that earlier in problem 3a, that log base 10 was written a special way. It's written as just logarithm. So these are log base 10, which can be found in the calculator next to the button for 7. So anytime you're in log base 10, you can evaluate with the calculator. So log of 1857, we can type this directly into the calculator. And this would be approximately, we'll round to 2 answers, approximately 3.27. Now we want to verify this answer. And to verify this answer, we would need to rewrite into exponential form. So if I want to rewrite this into exponential form, this would be base 10 to the 3.27 power, or approximately 3.27 power, and this should be approximately 1857. So I can do that in my calculator by doing 10, hitting the exponent, and then selecting that decimal representation. And this should be 1857, and it is approximately 1857. So we can verify that these are actually good approximations by rewriting into exponential form. See if you can find the approximate value for b. Hopefully you got a chance to find that value. So as we type this into the calculator, we get that this value is approximately negative 0. We'll round to 2 decimals again here, 59. To verify this, this is of base 10, so I could do 10 to the exponent that we found as our output and see if that's approximately 0.258, and it is. So this would be a good approximation for log base 10 of 0.258. Now in C, we can do the natural log. So we can use the natural log button here. So the natural log of 2 would be approximately 0.69. To verify this one, natural log is of base e. So we could do e to this given exponent that we found and see that that is 2. Same thing can be done in problem D, so go ahead and pause the video and see if you can find the answer for problem D. Hopefully you found an answer for problem D, and that answer would be approximately 1.28. So what we can see here is that logarithms and exponential functions are related to one another, being the inverses of each other. This looks like a good place to stop for today. So as always, thank you guys for tuning in, and we'll see you soon.